Hey everybody, today we're going to work on similarity lesson number 4. Now, I added the X, Y, and Z in those corners right there. You'll have to add them in for yourself. But what I actually want you to do is pause the video for a second, and I want you to try a magic trick. It says it right here. With one swipe of a pen or a pencil, I want you to take that triangle right there and turn it into 3 similar triangles. Okay, so I actually do want you to pause the video, and I want you to give it a shot. And then I'm going to reveal the answer and then why it is the answer, because a lot of people complain when I tell them that it works. So pause the video real quick and give it a shot. All right, so the answer to the question is this line right here. Now I'm going to call that point W right here, the point where that line hits that bottom right there. Let me explain why. Here's the deal. That line that I just created, it's called the altitude. And the thing about altitude is basically like the height. So it's like the height of a figure, but it must be perpendicular. So essentially what we've done here is we have created a right angle right there. Now, when I say it created 3 triangles, what I mean is we have one here, we have a second one here, and then the whole thing counts as the third. And they are all actually similar to each other. Now, sometimes people need to visually see it, so I'm just going to do one quick thing here before I move on and fill in the rest. I just want to actually show you what would happen if you took this figure, then there you go. Take a look. These are actually similar triangles. They don't necessarily look like it right away, but they are. And it turns out both of them are actually similar to the original as well. And this actually ties into what we talked about before when we talk about the different ways that you can prove that 2 triangles are similar. We talked about how you could either do angle-angle similarity, we could do side-angle-side similarity, or side-side-side similarity. All 3 of these have right angles. All 3 of these triangles have right angles. The first one does. The second one does. The third one does. All 3 of them do. So they all 3 have an angle in common. So the question just becomes, is there another angle in common? Because then we could use angle-angle. Well, if you look at triangle 1, angle X is both in triangle 1 and in the big triangle. That means I could say that triangle 1 is similar to the original because of angle-angle similarity. Now, if you look at triangle 2 on the right, angle Z is on triangle 2, and it is also on the original. So again, there's another angle that they share. So that means angle 1 or triangle 1 is similar to the original. Triangle 2 is similar to the original. And if both triangles are similar to the original, then that means they are also both similar to each other. Essentially, if that reminds you of a property from back in the day, it actually is the transitive property, sort of thought of in a different way. We learned back in the day that if angle 1 is congruent to 2 and 2 is congruent to 3, then that means 1 is congruent to 3. Kind of the same idea right there. Now, the theorem that describes this, if it sounds like I'm just repeating myself, it kind of is. I think we already did a pretty good job of talking about it, but the theorem is still necessary. The altitude to the hypotenuse, that's what we just did. We drew an altitude from the very top down to the hypotenuse of a right triangle. Gets a little bit wordy, so just be ready for it. It divides the triangle into 2 triangles that are similar to the original, and I'm just going to have to go down low here, each other. So they are similar to the original, and they are also similar to each other. Now I'm going to keep going. You can pause the video because that was a lot of writing. If you were to take this triangle and you were to label it XYZ, just like we had it before, and then we added in that point W that we just created, we could actually write a similarity statement that discusses all of them. So if we name the original one triangle XYZ, it would be similar to triangle, and now if we're looking on the left, we would have to say, well, triangle, the triangle on the left, X matches with X. They were the same angle. But then the right angle sort of changes position, and we end up with XWY. And this is a tricky visual, so you sort of have to, like I was doing before back when you saw the example where I just sort of pulled this thing off to the side and rotated it. That's sort of what we're doing, is we are just matching things up. So we're basically saying that the original is similar to this, and then it is also similar to the triangle on the right, which, as you can see from this picture, is YWZ. So the original is similar to XYZ, and it is also similar to YWZ. So there's a lot going on there, and I get that it's a really tricky drawing. So just work with me here. Draw it out, and if we have to look at it again later, we will. Now, why is that important? Why is that part of what we're talking about in this chapter? Well, what if WX was 4 and WZ was 9? Could we solve for WY? And at first, it looks like we don't really have enough information. But then we think about that trick that we just talked about. We could actually think of it as a proportion like we normally do. We could say 4 over X equals X over 9. So when you can change the way you visualize these problems, you can get answers out of problems that didn't seem like they had enough information at all. Okay? So again, we have two similar triangles in this picture. The key is we have to identify that. And then what we end up doing is we end up noticing that when we write our proportion, the X over here and the X over here, it's actually the same number. 4 over X equals X over 9. I'm going to put this drawing back over here so we can see what's going on. 4 over X equals X over 9. So essentially what's happening is this X is serving two purposes. The X is on both of the similar triangles. It's the base of one and it's the height of the other. Okay, now this comes up so much, it'd be really nice if we could come up with some sort of a shortcut. And this is where we use humiliating sound effects whenever I'm teaching it. Without having to redraw it, there's actually a pattern that we could just use over and over again. And I think about it as just going up and then back down. Now, this is where the weird sound effects are going to come in. Just work with me. The students who have had me long enough know it's coming, so it's just one of those things. Instead of having to pick up one of the triangles and rotate it like I've been doing over and over again in this video, we actually don't have to if we can remember this trick. We can just go, and then you follow along, just follow the arrow, and you get 4 over X. And then you go back down again, and you get X over 9. So if you can remember that pattern, then you never have to redraw anything. All you have to do is remember, oh, this is one of those where we go, and then back down again. Now, what's weird about this problem is when you actually try to solve it, the math isn't hard, it's just weird. X times x, a lot of people want to tell me that it's 2x. It's not 2x, it's x squared. And then 4 times 9, you probably know, is 36. So again, the reason kids get this wrong, generally they get it wrong because they forget that x times x is x squared. Then you ask yourself, hey, what number squared is 36? And we probably know that because it's a perfect square. The number is 6. So it turns out WY is 6. Now, this happens a whole lot. This type of problem comes up a whole lot in math, which is why we have a special name for it. Whenever you see a situation like this, this is called the geometric mean. Now, that is not the same as a regular mean, like an average. It's the geometric mean. It comes up here in our geometry class, but it comes up in a couple different places. It's a special term. And the way to figure out geometric mean, if you're ever just told, hey, find the geometric mean of these two numbers, I remember it was on an ACT problem once, so it's a good concept to know. All you have to do is do exactly what we just got done doing. Put the numbers on the corners, put x's on the other corners, and then solve. So in this case, x times x is x squared. 2 times 8 is 16. And that means x equals 4. So what is the geometric mean of 2 and 8? 4. We're going to do rapid fire. We're going to do a couple of these just to make sure you understand what's going on. If you had 4 over x equals x over 25, and you wanted to know the geometric mean, you cross multiply, or whatever it is that you learned is how to solve this back in the day. You get x squared equals 100. What number equals 100 when you square it? That would be the number 10. So what is the geometric mean of 4 and 25? 10. Sometimes the numbers are going to get really big, but it's still going to work out. 16 over x equals x over 64. A lot of people start freezing up. This is where a calculator is definitely going to come in handy. You end up getting x squared equals 1024. And then I know you can freeze up, like I said, but if you do the square root on your calculator, remember the opposite of a square is a square root. So if you don't know what number squared is going to get you 1024, take the square root of that on your calculator. You should end up getting 32. Now, the last type of problem that kids seem to have a hard time with is when you get a problem like this. Seems innocent enough. It's just 4 over x equals x over 8. Doesn't seem like a big deal. It's just going to be x squared equals 32. But then you realize, well, I don't know what number squared equals 32. If I try to do the square root of 32, I don't know it off the top of my head, and my calculator said it was a funny decimal. How can I break that down? How can I make it look a little bit better if I don't want to write it as a decimal? And then that actually goes back to something that you should have learned in Algebra 1, either a factor tree or by simplifying radicals by turning them into two separate ones and picking one that you know. Now, here's how you usually see higher level kids work through it. When you're young, you usually do the factor tree, and you probably remember those days. 32 breaks down to give you 4 times, that sort of thing. And you just keep going. But I think we can move past that. I think we can step up our game a little bit, and we can go the better way. The better way, the faster way anyway, is to take the radical, the square root right here, the square root of 32, and break it down into 2 radicals. Now, I don't want to pick any 2 radicals. I want to pick a perfect square as one of them. So it turns out 16 goes into 32, and it goes in 2 times. 16 times 2 is 32. Now, why did I pick that? I picked 16 because I know that the square root of 16 is 4. Now, I don't know the square root of 2. It's a funky decimal, but that's okay. The geometric mean of 4 and 8 simplifies down to 4 radical 2. Now, if you're not great at simplifying radicals, it's not a big deal because we all come from different Algebra 1 backgrounds. We all have different ways of doing it. So we'll do it this way one more time, and you can just sort of see what you think. And if you have trouble, that's definitely something that you can look up online, ask a teacher about. Every teacher is going to have their own perspective on how to simplify a radical, but this is the one that I'm giving right here. So again, we try to take the square root of both sides. A lot of times you get a problem like this where you do it in your head. Well, 4 squared is 16. The answer is 4. Can't do that here because it's 75. Now, I don't know the square root of 75, but I do know a perfect square that goes into it evenly, and the one that I'm thinking of is 25. And 25 goes into it 3 times. Now, why did I pick 25? Because the square root of 25 is 5. So the idea behind this method is you're taking something and turning it into a square root that you do know and a square root that you don't know so that you can break it down and write your answer in a little bit better of a way. Now, if you were to double check your work on a calculator, you would find out that the square root of 75 and 5 radical 3 do come out to the same decimal. Now, I know this isn't on the front of your paper. This last one I'm going to talk about is actually on the back of your paper, but I do want to bring it up. We have our magic trick, our little sound effect for going, whoop, whoop. What happens if the thing that you're trying to solve isn't in the middle? What if the thing that you're trying to solve is on the outside? And this one's a little bit trickier, but it's still a sound effect method. The way I do it personally, instead of starting on the outside for my sound effect, I actually start in the middle. And then I go up the side instead, and I go, whoop. So if you were to follow along with this arrow, that would give you 3 over x equals, whoa. Now see, that one's different. I always joke around. It's like me driving in the ice. I can't stop. I'm getting to that middle part back where I started, but I can't stop, and I go all the way through. So you go back down, but when you go back down, you go all the way through. Now, what is that total length down here? If I were to travel the entire distance, that means I would have traveled a distance of 3 and 9, which means I traveled a total distance of 12. So now we have x squared equals 36 because we cross multiply or whatever it is that we do. And it turns out x equals 6. All right, let's zoom in so you can see exactly what's going on here. I'm kind of running out of room, but I want to make sure you get a good view. So again, the method was you still go up, but you go up the side instead. You go, whoop. When you go back down, whoa, you go all the way through. All right, I want you to look one more time. We'll practice this, but we'll go up the other side instead. If you're going up the other side, we're going to start here, and we're going to go, whoop. That's going to give you 9 over y equals, whoa. And when we get to the bottom, we have to coast all the way through. 9 plus 3, we're doing the entire distance, which would be 12. When you try to break that down, you get y squared equals 108. Now, I don't know the square root of 108, but there is a perfect square that goes into 108. The biggest one I can think of, and you always want to use the biggest one because it'll save you from having to do this process again. The biggest one I can think of is 36, and it goes in 3 times, which means y equals, well, the square root of 36 is 6, and then I could just leave the radical 3 there. So again, it's another way of not having to redraw the triangles, because if it's up to me, I would rather not redraw them if I can help it. It's kind of cheesy. The sound effects are sort of silly, but I have found student after student, even at the end of the year, that tells me I remember those problems because I remember those sound effects. So just go with it and have a little fun. So anyway, hope this helps. Thanks for watching. I'll see you next time.